Asymptotes and algorithms, what you guys have forgotten since university. That's the idea anyway. So more specifically, what we're going to talk about is, we'll have a quick introduction. I'll tell you a little bit about myself, not very long because let's face it, it's not very exciting. We'll talk about what an algorithm is, all right? We have an idea in our heads what an algorithm is, but we'll just define it so we're all singing from the same song sheet right from the start. Then we'll talk about why optimization is important. And then I'm going to tell you that optimization of algorithms is child's play, right? It is easy, okay? This guy sitting in the front row going, this man's an idiot, right? There's no way kids can do algorithmic optimization, right? Well, I'll show you that they can. It's not something that's difficult. In our heads, we think that algorithmic optimization is difficult, all right? I'm going to show you that it's actually easy, and it's something we do naturally. And then I'm going to talk about the things that makes us think that it's difficult, right? The fact that we use mathematics to describe it, all right? And why we use it, and why that makes us think that it's a little bit difficult. Then I'm going to show you one tactic for optimizing an algorithm. Okay, there are a number, all right? I'm not going to try and confuse you and everything by showing you 7 or 8, okay? We'll talk about one tactic for optimization, and we'll give you an example of that, and hopefully we'll be able to carry that in our heads. And here's the thing that's important, right? This is the takeaway. This is the thing that's exciting about this session. This is the thing that I'll guarantee you, as soon as you leave here, you'll be thinking, you know, I need to get into the office on Monday morning and start to at least think about that kind of stuff, all right? It's why it's still important in the days of .NET, all right? Or the JVM, or any other framework that you happen to be using, okay? I'll explain why it's important there. And then I'll take questions. I'll take questions at the end, right? It appears at the end of the session, the agenda slide, because let's face it, you've got to put it somewhere, okay? But I prefer to take questions as we're going along. I will have questions at the end, but if you've got a question as we're going along, just put your hand up, all right? It makes it a lot easier if we're actually on the slide or in the middle of the demo where you've got your question, and it saves me having to fiddle around and try and get back to where we were, all right? Some speakers say, oh, I don't want you to do that. I want to save your questions to the end because I might answer your question in the very next slide, all right? Well, I don't care about that. Because if you have a question that I answer on the very next slide, then it makes me look like a genius, right? If I can say, haha, click, here's the answer to your question, all right? So I don't care about that, so jump in. All right, so quick introduction about me. This is me, my name is Gary Short. I'm a developer evangelist for DevExpress, okay? The evangelist is an interesting term. In the UK, it's a very American word, you know, being a developer evangelist for a company, because I work for an American company, Developer Express. In the UK and in Europe, that term is not used so much, and to the extent that I even had one guy in England ask me if I was a developer evangelist, does that mean I write software for God? Sadly not. Things would run a lot more smoothly, I can tell you, if I wrote God's software, that's all I'm saying. But I thought that was quite cute, all right? The most important thing about this slide is the 2 bits at the end. Okay, if you have questions and we don't have time for them here, or you don't feel you want to get in front of a microphone and speak about in front of all these people about your questions, that's not a problem. Drop me an email at garys@devexpress.com or send me a tweet at GaryShort. Hands up here if you're on Twitter. Okay, a few people, excellent. Feel free to follow me. Feel free to send me tweets. Feel free to engage with me that way. You're far more likely to get me to engage with you if you're on Twitter than if you send me an email. All right? It's not because I'm some sad IT dev guy who's always on Twitter. It's just that if you ask me a question on Twitter, it can only be 140 characters long. All right? You are far more likely to get a response from me if your question is 140 characters long than if you send me a 10-page email. All right, so we've got a lot to get through, so we're going to crack on. So what is an algorithm? This is it. It's really simple. It is not complicated. It's a finite list of well-defined steps, okay, to complete a task or a calculation, and that's it. Right? Nothing complicated. Everybody thinks algorithms are really hard, and they're dreamt up and refined by people with long beards who wear open-toed sandals. Okay? Algorithms are not complicated. They are just a simple list of well-defined steps to complete the task, and that's it. Nothing complicated there. There are simple ones. Let's have a look at a simple one. Let's jump in and show some code. If I can hit the right switch. Excellent. And there is. Oh, that screen's a little bit slow. Did you see that? Okay, so here we go. Let's look at this. This is a simple algorithm. Let's get this out of the way, because we don't really need that just now. And did I just close that completely as opposed to unpinning it? So here is a very simple, right, algorithm. Let's actually run it and have a look. Ladies and gentlemen, you're about to see what is, in effect, the most impressive demonstration that you have seen this week. Is that right? Okay. It pretty much is. Hey, my demos at least work. All right, they might be simple, but they work. All right, let's get rid of that. Beg pardon? It's all numbers. How can I misspell a number?
Not the numbers, the code.
Do I look like an English major to you? All right, so you get your first public warning. Okay, 3 and you're out. All right, so look, this is a really simple algorithm. All we're really doing is returning a list of squares of the first 5 numbers. All right, and when you have a look at this code, right, the actual business end of this code is only 1 line long. All right, you can't get much simpler than that. All right, but it's still an algorithm, a finite list of steps. All right, so the first step is we're going to return something. All right, that's number 1. So we're going to return something. What we're going to return is we're going to grab this array here. Okay, that's the second thing we do. And then we grab this select, right, and we create a projection. Okay, that's the third thing. And then we turn it into an array. That's the fourth thing. All right, so there's 4 steps there. That absolutely is an algorithm, even though it's dead simple. Okay, let's flick back to our slides. Click, click, click. All right, so there are simple ones. That was one. And there are complex ones, all right? So there are complex ones. There we go. So here's a complex one, all right? Basically, you can read the writing later, or you can have a look at it just now. But basically what it says is, prove that for a Pythagorean triple, a to the n plus b to the n equals c to the n is only true for numbers less than 3, okay? 1 and 2. So basically, everybody knows from school, right? Pythagoras' theorem, a squared equals b squared plus c squared, all right? You know that it doesn't work for cubes and powers of 4, 5, 6, 7, right? But the proof for that is a book, right? It's that thick. All right? Out of interest, does anybody know what that's called? Yes, sir? Fermat's last theorem. That's absolutely right. Well done, sir. And that is very complicated, all right? But there is no difference. Just because one's complicated and one is simple, all right? They are both still algorithms. Algorithms, in their nature, are not necessarily complicated. But let's look about one of the titles of this session. Why is optimization important? Optimization is important because the resources that we're consuming with our algorithms are finite, right? They can't go on forever. We will run out of disk space. We will run out of bandwidth, and we'll run out of processor power, all right? And so we have to optimize for the thing that we're interested in, right? Now, that may be, so back in the late 60s, early 70s, when the relational model came along for database design and that kind of thing, what we're trying to optimize for there was disk space, right? We're optimizing for disk space because it was expensive. Now, not so much. Now, what we normally optimize for is speed. I'm going to tell you right here and right now that the number 1 most important thing in the software that you write today is the speed that it executes. All right? Put your hands up if you agree with me. All right, not so many people. Cool, put your hands down. All right, let me rephrase that. Absolutely the most number 1 important thing that in software engineering today is the speed that your code executes, except for pretty much everything else. All right? So the kind of things that are more important, maintainability, right? Do we agree that maintainability is more important? If I write a really fast execution algorithm and I hand it over to you and you look at it and you go, I have no idea what that's doing, okay? And I say, you've got to maintain it, that doesn't help. Maintainability is more important. What else is more important? Yes, correctness is more important, right? And we can go on. Language choice is more important. And this is more important. That is more important. So why do I say it's the number 1 most important thing if I then give you a list of things which is more important? Well, the reason that is because it's a different kind of important, right? It's on the importance tree. It's just on a different branch, all right? And this is why. Because execution speed is the same as currency. So the more currency you've got, the more toys and more nice things that you can buy. You can go into your favorite electronics store and buy your favorite pieces of electronics. If you've got all kinds of currency, you can buy a flash car, nice house, swimming pool, all the rest of it, okay? It's the same with performance speed in your algorithms. If you've got an algorithm that runs absolutely as fast as it can, all right, then that lets you trade off some of that speed for the nice-to-have things, like language choice, for example. If we want something to run as fast as it absolutely can, we would write it in assembler, right? Anybody here ever written assembler? Put your hands up. Okay, a few people. Keep your hands up if it was fun and you enjoyed it. Okay, so not so many people, but still some, all right? Takes all sorts, I suppose. All right, but it's easier to write in a high-level language, okay? And if we've got fast execution code, we can give up some of that code for some of the nice-to-haves, all right? So that's why we optimize for speed, and I have gone the wrong way. Now, here we go. Optimization is child's play, right? Optimization is really simple. In our heads, we think that algorithmic optimization is a difficult thing, all right? Let me demonstrate that to you. Put your hands up if you've got a degree, a comp sci degree. Okay, hands in the air. Keep your hands up. Keep your hands up if you had algorithms and asymptotes in your degree and you understood it at the time. Okay, not so many people. Keep your hands up if you understand it now, years since you've left university. Okay, so there's still a couple of people. My first question to that is, why are you here? Are you just here to make sure that I'm right? Okay, you guys are going to jump up and go, no, no, he's wrong. All right, so did you see the number of hands go down? Lots of people with comp sci degrees who did this kind of thing. Not so many people understood it first time round, and then very few people have actually continued that, yes, I totally understand what we're doing here. All right? And this is because we think that it was difficult. It's actually child's play. Let me show you. Let's take this algorithm, all right? This is an algorithm. Remember, it's a finite step of instructions to get a task complete. This is the algorithm that my wife would like to use, okay, for our children having dinner, okay? She would like them to stop the current task, wash their hands, sit at the table, consume their food nicely, okay, consume the dessert, and then help with the clearing up, okay? Right about at the 2, 3, 4-year-old stage with kids, put your hands up if you've got kids here. All right, you guys will know what I'm talking about. Up until that point, you can pretty much tell a kid what to do, and it actually believes internally that it has to do what you're told, okay? Around about 2, 3, 4, it starts to realize that, you know what, I do not have to do that if I do not want to, okay? And even if I do want to do it, I do not have to do it the way you say I have to do it, okay? And this is how my 4-year-old daughter optimized this, okay? She paused the current game. Notice she doesn't stop, right? We all remember this from our childhood, right? The summer nights and the summer days where you're playing street hockey, all right? There's 17 people each side, all right? The game lasts from when the sun comes up to when the sun goes down, and it's the first person to 1,000 wins, all right? Those kind of games, right? Games are never finished. The games are paused. She sets her velocity to absolute maximum, moves to the table, takes 2 slices of bread, scoops up as much food as she can, and disappears out the door, all right? 4 years old, and we're already optimizing algorithms, right? We do it naturally. It is not a difficult thing, all right? It's not a difficult thing. Not only that, but it's not a skill that we lose in adulthood. It's not like one of the skills. So a lot of the skills that we have as a child, we completely lose, right? The ability to bounce when you fall over is one of them, okay? You fall off your bike as a kid, and you kind of roll around a bit, and you get up. You fall off your bike as an adult, and damn, it hurts, all right? But algorithmic optimization is not one of these things that we lose, right? We can do it as an adult. Let me demonstrate. Let's take this algorithm for the morning, okay? We rise, we shower. Devs, yes, we shower, right? Okay. All right, we boil the kettle, you make some tea. I know you guys are American, so maybe coffee, all right? We make tea, we toast some bread, we spread butter on it, we consume breakfast, brush our teeth, commute to work, blah, 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 that kind of thing. Okay. You can substitute what you do in the morning, but that's an algorithm, a set of finite steps for getting you out the door in the morning and off to work. Okay, this is a colleague of mine. Her name is Rachel Hawley. She runs the community side of DevExpress, so all you developers who are interested in using our tools and run user groups and stuff like that, you'll deal with Rachel Hawley, okay? If you follow her on Twitter, this is what you'll see. This is her avatar. Quite a nice-looking girl. One of her jobs, our unofficial job at DevExpress, is to be my nerd wrangler, making sure that I'm at the right place at the right time. This is pretty much how I see her most of the time, screaming at me for being in the wrong place at the wrong time or with the wrong presentation. Now, take that previous morning algorithm. Well, Rachel, she likes to watch Smallville with her breakfast in the morning. Okay? So she has optimized her morning routine so that she can see Smallville in the morning. All right? And here's the important part. She'll put the kettle on to boil, and she'll put the toast in the toaster, and she'll rush back up the stairs. All right? So already, we're talking about one of the tactics that we're going to use to optimize algorithms later on. Okay? This idea of recursion, this idea of doing 2 things at once. She doesn't boil the kettle and make the tea and then put the toast in and spread the toast, right? She's doing 2 things at once to optimize the time. Okay? So it's not a skill that we lose as an adult. And Rachel's not anything special. Let me demonstrate here. Put your hands up if you commute to work. All right. Keep your hands in the air if you have a best time for work, to getting to work that you know. All right. Keep your hands in the air if you're secretly impressed when you beat that time. All right. So most people. All right. So that is algorithmic optimization. We already do it. All right. We all know our fastest times to work. And yeah, you know, when we beat that time, yeah, we're engineers. We did that. All right? So it's not a difficult skill. The only thing, let me tell you, the only thing that's difficult about algorithmic optimization is the language that we choose to express it, okay? Because we use math. And as soon as we start putting in squirrely lines, okay, and funny little characters, suddenly in our heads, everything becomes difficult, all right? Let me demonstrate. C# programmers, put your hand in the air. All right, excellent. Put your hands down. The majority of people. You see C# code, you're quite happy. You understand what it's doing. All right? I put a piece of Perl script in front of you, right? It looks like your cat's jumped on the keyboard, right? Suddenly, that becomes difficult, right? You look at C# code, you look at Perl script, it might be doing exactly the same thing. To you, C#, easy to understand. Unless you're a Perl programmer, all right, you look at the Perl, and you think, this guy's going, no, that's me, that's me. All right, if you look at the Perl script, right, it's all squiggly lines, and suddenly you think, that's hard, right? Well, it isn't. To the Perl programmer, it's the same thing. It's dead simple. So don't let the fact that we use maths to describe this, and we use all kinds of horrible, squirrely characters and everything, confuse you into thinking that algorithmic optimization is hard, because it is not. Okay, so why do we use maths, right? So here's the thing. We use maths because who has heard the phrase, all right, it works on my machine? Right? Who has used the phrase, it works on my machine? Yeah, so pretty much everybody. Okay, and this is why. If I'm optimizing an algorithm and I optimize it on my machine and I say, this is fast, right? There are two main problems here. We haven't actually decided what we mean by fast. Fast is a relative term, all right? Secondly, my machine is not your machine, okay? My machine isn't your machine, and your machine certainly isn't my Android or Windows Phone 7 or your favorite brand of telephone, okay? Their computer is just the same as my laptop is, all right? And so we need to standardize what we mean by fast, and we need to standardize on our machine, okay? So that when I say this algorithm I've created is this fast, okay, you know it's going to be this fast. You have a grounding in what I'm talking about, okay? So in order to be able to do that, what we need is a model, right? Sadly, not one like this, okay? Sadly, what we need is a model like that, okay? A cut-down representation of something that we're going to be able to work with, all right? Now, our model has, let's describe the things that our model needs. So, model has a single processor. We're not going to cheat by saying, hey, my algorithm is really fast, okay? Because in my model, I've got 120 processors, okay? That's cheating, all right? One processor is all you get. It's going to have RAM, obviously, because we need some working storage, all right? And it will understand some arithmetical instructions like add and subtract and pop and push and all these things. All instructions are executed sequentially. Again, we're not going to cheat. We're not going to say, hey, my model does parallelization as a constant time operation, and so, hey, look how fast my algorithm is. We're not going to cheat, all right? You only get to execute them sequentially, and all instructions take constant time to complete. All right, what I mean by constant time is the number of things in the collection that you're processing has no bearing, really, on how long it takes to do. All right? I described that really well, didn't I? Let me give you an example, all right? It does not take any longer to divide 1 billion by 2 than it takes to divide 4 by 2, all right? Division is a constant time operation. Doesn't matter how big the number is, it takes the same amount of time to complete the task, all right? In our model, all of these arithmetical instructions are constant time instructions. So let's have a demo. Let's flick back to my code. Let's see if I can get this right. Okay, so I'm 2 for 2 for getting the demonstration laptop on the switch. That can only get worse. Right, so let's open up the solution. Let's have a look at our sort here. So we want this one. Actually, I didn't even, oh, I do know what I have to do. What I have to do here is to grab and set up as default. And then I have to find it, and here we go. It's the slow sort. Right, what I'm going to do is I'm going to give you a demonstration first. So in your mind, right, I want you to see how quick or how slow this was, so we'll compare it later on when I optimize it, right? You're just going to have to do it in your head. Okay, so watch this. Wow, well, you got that, right? You'll be able to judge how much faster it is than that later on. No? No. So this is why we use maths, right? Because I need to prove it to you. I'm going to show you an optimized algorithm later on, and do you know what? It'll sort the thing just as fast as that. And you'll go, what the hell? It wasn't any faster, right? But we'll use maths to prove that it was. Okay, so all we've done there is we have sorted some stuff, right? That is a technical term used in the algorithmic optimization community. Stuff we want to sort. Okay, so let's have a look. This is the algorithm that does the sorting. Okay, so we can see it has a loop, and it picks up a key, and it's comparing some stuff. All right, and it's swapping them around. This sort algorithm is called insertion sort. Okay, who's heard of insertion sort? Okay, brilliant. Who's only heard of it because they did it in college and they've never had to talk about it ever since? Yeah, but the most of us. All right, it's really hard to actually describe a sort algorithm by looking at code. I don't know about you, but I look at code, I don't see stuff happening, right? I see code that I can work with, but in my head, I don't see stuff happening. So I'm going to cheat a little bit. what we're going to do is make our lives a little bit easier and go to this fantastic site here. So on YouTube, okay, we can get, so this is insertion sort modeled in the median of dance. So if we just watch this, we don't have sound, but it doesn't really matter. You just have to imagine Hungarian music playing. Okay, so what you can see here is insertion sort, all right? What's happening is we're comparing two things, okay? And if it's smaller, it moves to the left, all right? So move to the left really means going to the bottom of the array. Now that's a lot easier, isn't it? We can see what insertion sort's doing now. We don't have to look at the code, right? Two reasons for showing you this. One, it's easier to visualize that stuff, okay? And the other reason is that the code, although I can show you in code, the code is irrelevant. That is the beauty of algorithms, right? The code that you choose to implement it in shouldn't make that much of a difference, okay? Now, quite frankly, that is enough of that. Okay, so let's get rid of that. Let's put the code back. Let's put the code back, he says, turning it off, and let's move back to our PowerPoint. Okay, so we're not doing too badly for time either. So, we've got our code, all right? Now we actually have to calculate the cost. And now we're starting to get into the realms of talking about maths, and people start to go, ooh, it might get a bit difficult here, all right? This is easy. Just like I told you algorithmic optimization was easy, we do it naturally, right? I'm going to show you that this kind of thing that you have to do for calculating how long it takes or how quick an algorithm is something that you do naturally anyway. So what we've got to do here is we've got to take for each line in our algorithm, we have to work out what the cost is, right? And we have to work out how many times we do it. And then there's a sum of the products of the cost and time, all right? So immediately I can see some people going, what? It's the sum of the products of the what? What? What did he say? Right? Don't worry about this. You do it all the time. In fact, you do something much more complicated than this, right? Naturally. Who here has been out for a meal in a restaurant since they arrived at TechEd? All right? Most people. What happens at the end? The bill arrives, okay? And what happens is if you have to split the bill, you have to calculate, all right, what each person's share is. And how do you do that? You take the cost, right, of the individual dish that they had, times the number of courses that you had. So did they have appetizers? Did they have entrees? Did you have the desserts? Right? And then you sum it up on the table, right, to get the total. And then you add a tip, right? And then you divide it down again to get each person's bill, right? This is easier than doing that, all right? Because there's no tip stage and there's no adding it up and then dividing it afterwards. All you have to do is do the product and add it up, right? The only thing that makes this complicated is if you look at this here, because we're not running on a physical machine, we're running on a mathematical model, we don't actually know what the cost is, okay? And because the algorithm can work with any size of input, so you imagine you've got a function, okay, and that function takes an array or a list of something, you have no idea how big that list is going to be, okay? So because we have no idea of how fast the thing is, and we have no idea of how many times we're going to have to do it, we have to start using letters, all right? So what we say is, the cost for the first line, we're just going to call it cost 1. And the cost for the second line will be 2, and so on through all the lines of the algorithm. Okay? And then we work out how many times we have to do that based on the number of things that are going to be in the list, and we'll call that n, right? Because we're developers, we're quite simple people, and n for numbers works for us. Okay? So as you can see, the actual incrementer inside the loop, right, has to be run n times for the exact same number of elements as you have in the collection, okay? The second line, all right, it's n minus 1 times, okay, and so forth. And then once you start to get into the loop, okay, you have to loop through, so it's the sum of how many times you have to do it within the loop, all right? So we start to have to use letters, all right, which is easy, okay, because we understand now it's just like calculating a restaurant bill, all right? A little bit confusing because we have to use letters instead of numbers, but still easy stuff. So I'm going to get that clicker right one time. Here we go. So the running time then for this algorithm is time for each statement, which is the product of the cost and the time, as we said. So for this one, it looks like this. All right? Now, exactly, you see that people start to laugh and they go, well, that's nonsense, right? But look, all we've got here is the running time it takes, right, for an input of size n equals, and these are just the products, right? It's the sum of the products. So C1 was the cost for doing line 1 times n, which was the number of times that you had to do the first line, okay, plus, because we're summing it up, C2, cost for line 2, times the number of times you had to do that, which was n minus 1. It's actually really simple when you see it like that, okay? So the best case running time, the best case for insertion sort. Does anybody know what the best case for insertion sort is, what that looks like? No? Well, okay. So these would be base classes. Yeah, absolutely, right? So if there's nothing to sort, hey, I'm done, woohoo. All right, but let's suppose that we do have some kind of input, and we're not talking about a base case. Does anybody here know what the best case scenario for insertion sort is? Sorted already, absolutely, right? It's already sorted is the best case scenario, okay? So if it's already sorted, we don't have to do so much work. If we don't have to do so much work, then there are not so many letters and stuff. And we can actually simplify this down to this, okay? This is what it looks like when it's already sorted. We have to do less work. We can actually simplify that using algebraic substitution to make it even easier. Well, it's not really easier. We've just moved everything around a little bit, and it looks like that, okay? Which is a function in the form an plus b, okay? If you don't believe me, there is the a. Oh, nice. See, Microsoft's scrubbing off my slides as we move stuff around, not to worry. So we can imagine that that's going to be underlined, okay? So that's the an part, okay? This, awesome, is going to be the b part, right? So that's an plus b, okay? So what we can say in this case is that the time taken to process an array of size n is a linear function in n, right? Now, it's easier for me to say that, right? But let's just prove it, right? Again, picture paints 1,000 words. What I've done here is I've substituted the number 2 for the letter A and the number 3 for the letter B, okay? And we can see that's linear. Anybody disagree with that? No? Perfect. Excellent. Which means the bigger n is, okay, the longer it's going to take to process, okay? Indirect proportionality, okay? Worst case running time. Anybody here tell me what the worst case running time for this algorithm is? Reverse sort, absolutely. When it is in reverse sorted order, because we have more work to do. Okay, and if we have more work to do, then now the time taken to run n looks like this, because we've got more work to do. Using algebraic substitution, we can move everything around so it looks like this. And it's a function in the form an squared plus bn plus c. All right? I will now score stuff out to prove that. Oh, that's even better. Right, so this is absolutely no use whatsoever. Okay, so that's all moved around. But we can imagine there that what I just did was I underlined all of the parentheses before n squared, and that is your a. All of the parentheses in the second part before the n, which is b, and everything in the parentheses afterwards, which is c. Okay? I can prove that. So now we can say that the running time, if it's reverse sorted, the running time for an array of size n is actually a quadratic function in n. Again, let me just prove that. Okay, if I substitute the number 2 for A, the number 3 for B, and the number 4 for C, we can see that sorting out the resolution is actually squashed up a bit, but we can see that that is a curve, okay? And we know, because we're smart people, that something that curves, right, goes up quicker than something that's a straight line, okay? So this is going to take a longer time. So now we have managed to get one of our goals. Tick. I can prove to you that it runs faster, okay? Because either by writing it down like this, an plus b, I can say that's going to be faster than an squared plus bn plus c. I can either just prove it by writing it down like this, or I can prove it by showing you the pictures, right? If I say, look, this curve goes up faster than this line. So now already, all right, I can prove stuff. You don't have to look at the demo and go, oh, yes, I'm going to remember that speed. And look at my demo next time and go, oh, yes, that was absolutely faster, right? You don't have to do this. I can prove it to you. Okay? Another reason why that is important, okay, we'll get to actually in a minute. Can we make this notation more readable? All right? I don't know about you, but I'm not really comfortable speaking to my line manager about the speed of my algorithm and saying, hey, it's an squared plus bn plus c instead of an plus b. Yeah, great. That doesn't help me. All right? We need to make this notation more readable. All right? Luckily, we can do that. We're going to use something called asymptotic notation. All right? How many people have heard of asymptotic notation? A few people. Excellent. It's also called big O notation. Who's heard of big O notation? Right? So more people. Right. So and that's the more common name. Okay, big O notation. So what we can actually say is we can make the argument, and it's actually true, okay, that for functions in these forms, all right? If n is sufficiently large, and that used to be the get-out clause for algorithms, you know, if n is sufficiently large, okay, the largest term of n dominates the function. Okay, so if n is a billion and these things, right, and a is 2 and b is 3 as it was before, right, you've got a billion and 2 and 4, right? Who cares, right? The term of n completely dominates that function. And so we can make the argument, we can say, do you know what, we're going to ignore everything else. And what we get away with saying, because if n is sufficiently large, it dominates the function, okay, we can actually say, do you know what, the running time for n, although we say it's an plus b, okay, it's actually, we're just going to call it big O-n. Okay? And we're going to say for the other one, it's big O-n squared. Right? And now we're talking much more simplified notation. Okay? Much more simplified notation. I'm going to have a little side note here about the misuse of the word equals. Right? We say, right, when we write it down, we don't actually say, when we write it down, we say, the time taken for n is an plus b, and that equals big O-n. It doesn't equal. Okay? It's what Donald Knuth calls a one-way equality. Okay? Whilst it's true to say that an plus b equals O-n, it's not true to say that O-n equals the function. Okay? It's a one-way equality. It's like saying Gary Short is a man, but not all men are Gary Short. Okay? Same kind of thing. So we don't, although we write down equals because we're pretty lazy, we just can't be bothered to make up another mathematical symbol for is, okay? We write it down as equals, but we actually say is. So when we're reading that out, we say running time t of n is big O-n, not equals big O-n, okay? But that's just a slight aside. So now we can actually say that insertion sort, thank you very much, we can say insertion sort, best case is big O-n, and worst case is O-n squared. Now when we're talking about these kind of things, it makes life a lot easier when we're talking to our boss and our customers and those kind of things about the speed of our algorithms, okay? So we've simplified that. So now we're simplifying things all the way down. We're telling the story, right, that algorithm optimization is not difficult. We do it as a kid. We don't lose the ability to do it as an adult. The only thing that makes us think it's complicated is the fact we use maths, and we've simplified the maths down to something from, there was a horrible line of numbers and letters, down to something which is just simply an O and an n squared, okay? But we're only interested in the worst case. Right? Why are we only interested in the worst case? Yeah, because that's the one, it's easy to make an algorithm go fast by giving it its best possible case. If I told you, right, so the best possible case for insertion sort, we've already said, is if it's already sorted. Okay? So if I jump in there and say, hey, I've got a great sorting algorithm, provided you pass it an array which is already sorted, okay, it's really fast. Well, that doesn't really help you. So we're really interested in the worst case because we want to know how fast it goes given the worst possible case. Okay? So what we actually say is that insertion sort is big O-n squared. Right? Even though in best case scenario it's n, we say it's a big O-n squared algorithm. Right? Who's heard that term before? Okay. Who understood it fully before I explained that? Oh, not so many people. Okay, so that's good. So some people have learned something. Excellent. And we're only halfway through the session. So let's optimize this algorithm now. All right? Let's make it go faster. All right? So what did we do when we were kids? So let's take the simplest possible thing. When I was 4 years old, how did I make things go faster? And what I did was I divided and conquered. Right? And that is the name of the technique that we're going to use, divide and conquer. I took the whole thing that needs to be done, okay? I made it into something, lots of little things which were easier to do. I did those preferably at the same time, and I joined everything together at the end. Right? That is the technique that we're going to use here. So let's have a demo. Let's switch across to my demo machine. Am I going to get this right one more time? Yes! Okay. So we're going to do two things here. We're going to jump into the optimized sort up here. We're going to make that the startup project. Okay. I'm going to find it. There we go. It looks like that. I'm going to run it. There you go. Now, did you see how much faster that ran compared to the first one? All right? Perceptively, that was easy, wasn't it? Right? That was easy to do. Okay. No. Now you see why we need to prove it with maths, right? If I said to you, which one was faster? You go, they were both the same. Okay? But now I can actually prove to you with maths that this one goes faster. All right? So let's get rid of that. Here's what this one does. Here is really the most important part. Okay? We divide the array up into two halves, okay, and we call recursion, okay, we call the same function with the subparts. All right, that's what we do. Now again, we can go through this code, okay, and I can show you it, and you'll go, yes, that's cool, Gary, that's code, thank you very much, okay, I'm not really sure. So it's time to speak to our Hungarian friends again, and they're going to show us merge sort. This is what's happening here, okay. We start off with an array. Use it this time. And we split it in two, okay? And then we solve each half of the problem, okay? I understand there's only so much of this that we can take, okay? So we're not going to watch too much of it, but you can see what's happening, all right? You can see, and please go to YouTube and in your own time enjoy the Hungarian dancers, right? But it is much easier to visualize what's happening now. You can see we solve one side, and when you watch this all through, it's 4 minutes long. How you can make this last for 4 minutes, I have no idea, okay? But it goes on for 4 minutes, and you can see that we solve one side, we solve the others, but let's jump forward a little bit to see what happens at the end. Okay, so here's the important part. We take stuff from out. We take one from each side and we see which is the biggest. Okay? Whichever one is the biggest, which is the smallest, goes in the right place in the array. Okay? That's quite enough of that, I think. And that's much easier to visualize than what's going on in code. And as I say, please go to YouTube, look up these things, and enjoy the Hungarian dancers explaining the two different sorts to you. Okay, so how fast is that algorithm, right? It's a little bit difficult now, because remember before we were adding up the products. So we're summing up the products, and that was easy for that kind of stuff when we're going through everything sequentially. But now we've introduced recursion, and things get a little bit harder. So what are we going to do with that, all right? So this is what we actually did. We did merge sort. For those of you who didn't immediately recognize that code as being merge sort, and who didn't, I mean, because obviously we have that imprinted on our brains. Okay, what we actually did was we did the divide. So let's actually see what happened there in terms of the cost, okay? It computes the middle of the array. Now, we already spoke about this at the start. What is that? It's a division, which means it's what in terms of time? It's a constant time. Excellent. It's a constant time operation. Okay, so we can say that the dividing of n, regardless of the size of n, is a big O1 operation, okay? It's constant time. And to be honest, if it's constant time, do you know what? We can just forget it. Okay, then we conquered it. We conquered the problem, i.e. we solved for the two different halves. Boom, boom, boom. Was that me? I was a little bit worried. Okay, so recursively we solved it, right? Which means we solved the two n/2 sized problems, okay? Each contributing 2t n/2, right? And then once we solved those, we combined the two things together, okay? That's what we did when we were kids as well. So the combined step is linear, okay? The more that we have to combine, so we're taking one list here, and we're combining them, which means it's a linear thing. The bigger the two lists are, the longer that's going to take, okay? Now that means that adds, that step is linear, so it adds big O n to the total. Okay, so what we've got here is, in the worst case, okay, it's going to take us 2t n/2 plus on to do that. Now, who would feel confident going to their boss and saying, hey, I've designed an algorithm, okay? How fast is it? Well, I'll tell you now. It's 2t n/2 plus big O(n). Right? Doesn't mean anything, all right? So we need to solve that. We need to make it more simple, okay? So what we're going to do is we're going to use the master method to solve this recursion. Who's heard of the master method? Nobody. One person. One person's not sure. He's like, but if I'm going to be the only one, I'm not putting my hand up in case he asks me a question about it. So I'm going to half put it up to say, I'm clever, I've heard of it, and I'm going to put it down real quick before you ask me a question. Okay, one person in the room. That means if I explain to you what the master method is, right, every single person, apart from you, smarty pants, okay, leaves this session learning something. How cool is that? All right? So what is the master method? It is a recipe for solving recurrences. Okay, everybody, does everybody know that the name for when you use recursion inside your software, what you actually get in terms of math is a recursion? All right? Who knew that? Nobody. Win, right? Everybody leaves learning something. Okay. So we're going to solve the recursions. Okay, now they happen to be in this form, right? I'm not going to read that out because you can read faster than I can speak. They need to be in that form, okay, where the constant a has to be greater than or equal to 1 and b has to be bigger than 1. The function that we get at the end has to be asymptotically positive. Isn't that fantastic? This is another thing why we find algorithmic optimization, we think it's difficult, is because maths geeks love big words, right? Asymptotically positive just means it gets bigger, okay, instead of it gets smaller. Why they couldn't just say that, I have no idea, okay? But asymptotically positive means it gets bigger. Right. However, our function, okay, 2tn over 2 plus big O n, is in that form, so win. So we can use the master method, all right? So let's do that. How does it work? It works, and this is why I love the master method. It works with functions in this form, all right, which we've got, okay? It's a comparison. There is no maths involved, okay? No counting, no subtracting, nothing like that, all right? To use the master method, there is no mathematics involved, all right? So it's gotten simpler straight away, okay? All we do is we take the little function at the end and we compare it with n log b of a, all right? Where we've already said what b and a is. So it's a comparison. We just look at the two things. So what we see here is the larger of the two determines the solution. And intuitively, that's right. You know, intuitively, we say, just as much as we said previously, if n is big, then it dominates the function. Just as intuitively as that, here, the bigger of the functions, okay, determines the solution. So, if n log b of a is larger, then that is the solution. If the function is larger, then that is the solution. And if they are equal, then we multiply by a log factor. So we get big O f of n log n, okay? So in our example, in our specific example for merge sort, we're in case 3, all right? So in the worst case, merge sort is n log n. Worst case, merge sort is O n log n. Does anybody happen to know what the mathematically fastest, a sort algorithm that does a comparison between two things and swaps them around, the absolute fastest it can go? Does anybody know? Mathematically. Nobody. Awesome. So you've learned everybody's learned two things today, okay? It is n log n, okay? If you think about it, it's a binary tree. You're taking two things, and one's bigger and one's smaller, so you create a binary tree. Because it's a binary tree, n log n is as fast as it can possibly go. So this is awesome. The absolute worst case scenario for merge sort is the fastest it could go, all right? It's much better than insertion sort, which is n squared. Okay? So we have improved our algorithm. We've improved our algorithm to being the theoretical fastest by doing something my 4-year-old daughter does. All right? How cool is that? All right? Algorithmic optimization can't be any easier than that. Okay? We've improved it to its theoretical maximum by doing something a 4-year-old does. Okay? Good stuff. This is a proof, right? You don't have to take my word for it. Here is what n log n looks like on the red line, okay? And here is what n squared looks on the green line. So now when I say one's faster than the other, you can see it because you can see it in a diagram, right? It's easier to understand. Great stuff. Now, .NET handles all this for me, though, doesn't it? I don't have to worry about that, okay? I use the .NET framework. The people who work for Microsoft must be smarter than me. All right, put your hands up if you think you're smarter than the guys that work on the .NET framework. Okay, one guy at the back. Are you Anders Heiselberg? No, excellent. Thank goodness for that. Okay, so, but the .NET handles this for me. Well, not so much. Not so much as you think. This is the takeaway. This is why this stuff is important to carry in your head, right? At least have a thought about it. Let's take the very common scenario of using a list T add. Here we can see a very quick code demonstration. We create a list of ints, okay, and we add one by calling add. Very simple, right? Who here has used code like that before? Everybody who programs in C#. Absolutely. It's the most common collection, and add is the most common thing to do to it, okay? Let's break open the code using your favorite code inspector, okay, and have a look to see what it actually does under the hood. So halfway down there, you'll see a function called ensure capacity. Okay, ensure capacity for the capacity that I've got at the moment plus the one I'm trying to add, it says. Okay, let's jump in and see what that does. Okay, what it does is it says, if it's just been created and I don't have any size yet, I've not been asked to add anything. If I'm adding something for the first time, then I'm going to return you 4. Okay, that's an arbitrary number. I'm sure there's a great idea. There's a great reason why it's 4. I don't happen to know what it is. Okay, but if it's the first time we're trying to add something, make the size 4. If it's not, then double the size that you already are. Okay, so you have an array. It's this big. Okay, we're going to make it twice the size, regardless of what the size was. Right down at the bottom, you'll see a function there called this, you'll see a property, which is called a capacity. Let's have a look and see what that does. And here's the killer. All right, 2/3 of the way down there, you'll see array.copy. Okay, when we copy stuff from the old array into the new array we've just created. So there is a growth algorithm for growing the underlying array that's held in the list. Okay? Does anybody know what kind of time it takes to do an array.copy? Okay, it's order of n. Well done, that man. Yes, it's order n. Okay, it's linear. The bigger the amount of stuff we've got to move, the longer it's going to take. All right, so from that point, knowing that, right, we know that we're going to have a problem when we start adding big collections. Okay, if we get fed a collection and we're running through a for loop, right, to add them, we know that at some point that's going to start to hurt us. That array growth is going to start to hurt us. Let's have a look at the other one. Okay, the other way of adding is to add a whole range at one time. Okay, again, very simple piece of code. We create a list and we add a new array. We add range. Who's used this piece of code? Okay, some people, but not so many. All right, it's not so common. Let's have a look at what happens here. What happens here then is that add range calls insert range. An insert range does all this kind of stuff. Look halfway down, we find it takes the collection, okay, and then 2/3 of the way down, it runs ensure capacity. Right? We already know what ensure capacity does, okay? Whoops, let's go back here, sorry. We already know what ensure capacity does. It does that array growth, but this time it does it one time. All right? The algorithm has a look to see how big is the collection I want to add. All right? It does the ensure capacity to make sure it's got enough time, and it does it one time. Okay? And then it adds everything. So what kind of performance implications does this have? So here's a little test. Let's test something. Okay? Sometimes with an algorithm, you don't actually have to sit down and do the maths. Right? Sometimes if the algorithm doesn't actually show its advantage until n is massive, right, it's not really possible to do. But sometimes you don't actually have to do the math. Sometimes you can just test it. And that's what we're going to do here. So what I've got is a little test code here. It's a little data provider. I call this method called getData, and I pass in an int of the size of the collection I want it returned, right? And that allows me to fill in, okay, orders of magnitude. So I can say, give me an array of size 10, size 100, size 1,000, okay, and I can go up like so. And then I've got 2 little tests, right? I use the nice stopwatch provided by the nice people at Microsoft, and I use an add, and the other one I use add range, okay? And when I fire these off, this is the kind of thing I get, okay? So you can see for the first 1,000 items that I'm adding in a loop, it doesn't really make any difference, okay? By the time we get to 10,000, it's starting to make a bit of a difference. By the time it grows bigger still, to 10,000, 100,000, that kind of stuff, we start to get a big difference in the speed that it takes, okay? And this is why it's important, okay? Understanding algorithmic optimization is important because if you just assume that the guys at Microsoft are smarter than you, and let's face it, to be honest, they are, but what they're building is a general framework, okay? Nobody lives in the general world. And it's a good job, okay? And here's an example why. Because in the general world, right, who plays the lottery here? All right, so in the UK, we have this lottery, all right? Statistically, in the general world, all right, you have more chance of a 747 crashing into your house than you do of winning the lottery. And yet every week, someone wins the lottery. In the general world, where are all the crashed planes? That's what I want to know. Okay? But that doesn't happen because we don't live in the general world, we live in a specific world. And the exact same is true here. Okay? We live in a specific world. They've got a general framework. Right? So generally, you know, everything works fine. But specifically, you need to know, what is it going to mean if I'm adding a large collection? All right? You need to know that you have an algorithmic problem, okay, for large values of n. Okay? Your code runs slowly. Okay? You can't just assume that it's going to run absolutely as fast as it can. Here's another example. Who knows what the sort algorithm is that's used inside list.sort? If you do list.sort, who knows what the algorithm is? Say again? It is not. It's not merge sort either. It is quicksort. Yes, well done, that man. Okay, it is quicksort. It's quicksort because that is the best, and here's that phrase again, general purpose algorithm. Okay, for the general case, quicksort is the best to use. Now, we've already said that merge sorts runs at the theoretical speed, so you think to yourself, well, merge sort must be the best one, right? But so does quicksort. Quicksort runs at that theoretical maximum as well, but it has better memory management issues and that kind of thing. Okay, so it's actually better over a longer period. And that is why Microsoft uses it, because generally, it's the best algorithmic sort routine. But again, we live in the specific world. And in the specific world, all right, there are certain cases which will absolutely kill quicksort. All right? As an exercise, when you go back to the hotel tonight or when you get back into the office on Monday, look up on the internet, quicksort killer. All right? I love that. Quicksort killer. Okay? And it will show you all kinds of algorithms and lists that you can put into a quicksort that will absolutely kill the performance and drive it right down. Okay? Now, I'm not suggesting for a single moment that you're going to sit down and do all kinds of maths, right, and say, oh, yes, it's fine to use quicksort at this point, or no, actually, I need to do my list, I need to sort my list in some other way. Okay? What I am suggesting is, bearing in mind what you know here about algorithms, right, look at what the quicksort killer scenarios are, okay, and then understand what kind of implications that's going to have on your code if you're using list.sort. Okay? Then you will know in your head that if you come across a pattern that looks like that, you're going to think to yourself, now, actually, I need to be thinking about something else for my sort algorithm. Because if I don't, then for some significantly large value of n, okay, that's going to get really complicated. So you need to have a backup plan. You need to know what you're going to do. All right? And if you say to your boss, this is what I'm going to do, and your line manager says, well, why don't you just use the sort algorithm that's available, you now know how to do the maths as well. You can actually prove to him that you could be in trouble. Okay? So this is why this stuff is important to remember in the framework. Okay? The guys at Microsoft are smart, but they are creating a general framework. You have to have an understanding of this algorithmic thing. A lot of people seem to have forgotten that since university because, well, we think the framework is going to help us. Right? It does, but it's really important that you understand what the algorithms do so that you understand why your code is running slow. Okay? Because, of course, there are all kinds of tools, there are profilers and all the rest of it, but that will only tell you where the problem is. It won't tell you why or how to fix it. It will say, hey, guess what? Right? Your sort algorithm sucks. Right? All of your performance bottleneck is in that sort. But without an understanding of algorithms and why the quicksort isn't working for you, you won't actually know how to fix it. Yes, sir? Yes. The heap sort is usually so the rule of thumb is use quicksort. If quicksort's not working for you, use heap sort. And if that's not working for you, sit down and do the math. Right? There is not. Okay? Because, you see, there we go. It's a general framework. Okay? So, what we've learned in this session, right, we're just going to have a quick summary before I tell you something that I think is quite important as well, but I want you to hold on to that before you go. Okay? We know why performance is important, right? Because performance lets us choose the best stuff. Okay? We can say, my performance is good enough that I can use C# instead of assembler. All right? Performance is important. Optimization comes naturally to us, right? 4-year-old kids can do optimization. It's not difficult. It's not a skill we lose as an adult. right? I've demonstrated to you. In fact, you all proved that you do it yourself with the commute to work time, right? So we all know that we can do algorithmic optimization because we all do it. Okay, we've learned divide and conquer, all right? To be honest, we didn't learn divide and conquer in this session, right? Because it's the thing we do naturally, okay? We do the divide and conquer, but we managed to put a little bit of rigor into it so that we understand why it's better. We've understood that the running time is the sum of the product and the cost of the execution, and we know that that is not something to be scared of because we know that when we pay a restaurant bill, it's something we do all the time. We learned that math syntax makes all this seem scary, okay? It's not. The squiggly lines are not anything to be scared of, all right? Because under the hood, once we understand that, it's really simple to get down to what we're actually doing. And it's easy to simplify using the asymptotic notation, okay? That makes life easy for us. And the crucial thing we learned, okay? This stuff matters even in the days of .NET or any other framework that you're using within .NET. Okay, or anything else that you buy in a third party. Okay, before I take questions, and I will take questions in a moment or two, I want to go back to a phrase that we've used previously, and that phrase is, for significantly large values of n. Okay, and it used to be a get-out clause, right, for algorithmic optimizers. You know, these guys with the beard and the open-toed sandals that work in universities, right? Nobody cared, really, for a long, long time what they did. And do you know why nobody cared? Nobody cared because the speed of chips, right? Moore's law always outdid the growth at which n was going. So n was getting bigger. The amount of data that we have to process was getting bigger and bigger all the time, but the chips were getting faster and faster. And it allowed us to be lazy coders in terms of algorithmic optimization. Because we could get away with using a slow algorithm because the chip underneath that it was running on was getting faster and faster the whole time. Okay? Those days have gone. All right? You can argue about whether or not Moore's law has gone from chips now or whether it's almost gone, right? But there is no doubt that it's fading. So these days, right, of being able to rely on Moore's law is also going. So that's one reason why this stuff is important, right? Because for in the future, we're going to have to use divide and conquer. What is divide and conquer called when we look at actual chips? Okay, multiple cores. That's just divide and conquer. They had a single chip, all right? The pipeline is full. What are we going to do? The same thing we did when we were 4, right? Guys at Intel thought they were really smart, right? They did something my 4-year-old does. Okay, they said, well, we'll divide and conquer, right? We'll put more cores on the chips, right? But that means what does our algorithm have to do? Our algorithm has to be, okay, capable of being parallelized. Parallelized? Parallelized. Why is that word so difficult, okay? It has to be able to do lots of things at once, okay? And not all algorithms are, right? So this divide and conquer thing for optimizing algorithms is one of the most important tactics, right? Because it helps us with parallelization, all right? Not all algorithms are parallelizable. Remember we said that an algorithm is simply a finite set of steps, right? How about having a pregnancy? That's a finite set of steps, right? We'll not worry about what happens at the start, all right? But, you know, thereafter, other things happen, and at the end, you get a baby, all right? You cannot take 9 women and have a pregnancy in a month, okay? You can't do that. That is an algorithm which is not parallelizable, all right? And so you have to, and so that's one reason why this algorithmic optimization is going to become important again in the future, okay? Because we're not getting the benefit from the chips. And the other one is because of what we like to call web scale. Okay? Before, the amount of data that it took before the sort algorithm, I mean, I could put a lot of sort algorithms, right? Like the one we had, insertion sort and merge sort, and to all intents and purposes, for the amount of data that I could throw at that, they would be the same. And so it allowed us to be lazy programmers and go, well, you know what, it doesn't really matter, right? I'm not going to have that much data in my sort algorithm. Those days are gone now, right? If you're looking at the billion-dollar companies of the future, sorry, of the past couple of years, who doesn't want to be involved in a billion-dollar company? Okay? They're all Google, they are Twitter, they are Facebook. They're all dealing with huge amounts of data, right? As developers, we want to be at the cutting edge, right? So now we do have huge values of n where that really matters. And that is why algorithmic optimization is important, okay? So it's important for 2 reasons, all right? It's important because we're getting away from Moore's law. It's important because we're starting to work with bigger and bigger data. And the third out of the 2 reasons, whoops. Okay, so let's go on to questions. Does anybody have any questions about what I've talked about? Anything they're not 100% clear on? Yes, chap way at the back where I'm not going to be able to hear him. Do you want to come up and stand in front of one of the microphones so we can point and laugh later? No, it's not on. Awesome.
I'd like to know.
Yeah, come here, stand at the microphone, and then shout at me anyway, like you could have done from back there.
Where does this fit into the development process? When you're developing standard enterprise applications, is this, if you get the good luck and you have an architecture team?
He said that with such sincerity. The good luck of having an architecture team.
Where does this all fit?
Okay.
Who does the work?
Oh, absolutely. So, we all know about premature optimization, right? And we'd be stupid to jump into this straight away, okay? But what you want to do is you want to have an understanding of where you don't necessarily have to come up with the solution, but you have to know where your bottlenecks are going to be. So you say, well, here's my architecture, okay? And I think that my data growth over the lifetime of this application is going to be this size. And with the architecture that I've got, I could probably live with that, and I could probably live with a little bit more, all right? But you have to have a plan for what you're going to do if it gets bigger than that. You don't have to have the actual solution written down and coded and ready to go, right? But it's good to at least know what you're going to do. Okay, so you're going to know, so for example, and you don't always have to scale in terms of algorithmic optimization. Okay, there are other optimizations that you can have. You know, you can just put in a faster chip. Sometimes that'll get you there. Okay, you can put in a data farm instead of a single SQL server. Okay, these are always more cost effective. Okay, it's the difference between scale out and scale up. Okay, so scale up is putting in bigger and better hardware. Okay, scale out is actually chopping that down into parallel tasks and making smaller. It's the divide and conquer. Okay, scale up is always cheaper, but it's finite, it's limited. Okay, there's only so much benefit that you can get. All right. So to answer your question, it's done maybe at the architect level or at the lead software developer level. Okay, you don't have to have the full-blown solution right at the start, but you have to have an idea of the boundaries. Okay, it'll work up until this point, and thereafter, we're going to be in trouble. So we know what we're going to do. At this point, we're going to look at scaling up as far as we can, and then we're going to look at divide and conquer within our actual algorithm, and we're going to parallelize that out. Okay. So does anybody else have any questions that they want to come up to the microphone that's not on and shout at me? Okay? Yes? No? No. All right. Let's do the final little slides. You guys will all know about this, I'm sure. Who has not seen this slide already today? Where have you been? Excellent. Okay, so this is stuff that you need to know. Okay, there are more resources here. All of this stuff is going to be online. This session will not be recorded, all right? So those of you who were not here, you will never see it, okay? Please, please, please do not forget to complete your evaluation form, all right? One, it's good for you because you could win one of these fabulous prizes, okay? Two, it's really important for Microsoft because it helps them improve the conference, and it's really, really, really important for speakers, right, to get your feedback, okay? So please fill this in, all right? If you enjoyed the session and you learned something, right? My name is Gary Short. If you thought I sucked, my name is Scott Hanselman, okay? Please remember that. Okay, so we'll finish there if there are no other questions. If there are questions, if you were just too shy to come up at the microphone, which isn't on, and shout at me, okay, please come forward and see me now as I'm packing up, or later on at the attendees party afterwards, okay? If you then don't think of a question until you're going home, please email it to me or send it to me on Twitter. Okay, thank you very much for attending, and I hope you've all learned something.